I cannot take distance also because distance is a scalar quantity, displacement is a vector quantity. I need analogous of displacement. When mass expressed in rotational sense, it is indicated as moment of inertia I. So thin circular ring of radius r and mass m. So the axis is passing through the center and perpendicular to its plane. So with that same logic, we can say that for a solid cylinder where completely mass is filled. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to learn a new chapter, that is System of Particles and Rotational Motion. It is a long chapter, but what we are going to do is that we are going to focus on the important concepts and we are going to do the important derivations also. It is not like it is a compressed, juiced version of the NCERT textbook, but everything you need from an examination standpoint of view will be discussed here. So let's begin. So let's start with the heading itself, System of Particles and Rotational Motion. So what exactly is a system of particles? What is that indicating? So let's say that I am taking an object. Let's say this is a cube-shaped rock or a square-shaped rock. Some object is there. Now, this particular object is made up of individual particles. That is, I can say that, okay, there are millions of particles that is inside this particular box, randomly distributed. So if I take random one particle, I can say that, okay, this is particle 1 which is having a mass of m, or simply we can say that that particular particle is indicated by m1 because it is a mass particle indicated by the letter 1. So that's the first particle. And there is not just 1, 2, 3, 4, 5, but there is n number of particles in this particular system. So when I move this particular system, that is, if I apply a force onto this particular system, the entire system is moving. Each particle on the system is moving. So this particular system means whatever I am considering here, this particular object is made up of n number of particles having masses m1, m2, m3, m4, etc. Imagine it like this. The simplest way to imagine a system of particles is that you're building a sand castle. So you're going to the beach, you're building a sand castle. Let's say this is a castle. It's not a castle, but let's assume that, okay, this is a castle. So if this is a castle, then it is not actually made up of one individual material. It is thousands of grains of sand combining together to make this particular structure, which means there are there are millions of sand particles within this particular sand castle, which means each particle on that particular castle, that is, each point will have a particle. So it is made up of millions of particles. This system, this sand castle, system is made up of n number of particles. So if I say that, okay, one such particle is having mass m and I am indicating it as 1. It is the first particle. So I am saying that one particle has mass m1 and it is made up of n number of such particles. Then I can say that the entire mass of this particular system is equal to the entire mass, let's say that is capital M, that is equal to m1 plus, m2 plus, m3 plus, etc. up to mn. If there are n number of particles, there will be n number of additions. So again, we can write this simply as summation over I is equal to 1 to n. That is, we are starting from 1 and we are ending in n. So n number of particles are summed together. So generally we can say that it will be equal to mi. So if there are n number of particles, we can sum them all together. Then we can say that, okay, the sum of all particles will give you the net mass of that particular system. So again, a system is made up of n number of particles. That is point number 1. So that is about system of particles. Now point number 2. What is rotational motion? So it is system of particles and rotational motion. So we just figured out what system of particles means. It is just a bunch of particles that is coming together to form a system. So again, now the second thing is, what is rotation? So what is rotation? You might have seen objects spin. You might have seen the earth rotating in some animation. You might have seen a ball rotating. So what exactly is rotation? Is it just something spinning? How can you define spin? You might say that, okay, rotation is just something spinning. So how do you define spin? Or how do you define rotation? How do you define rotation? Sir, the wheels of a car is spinning. The wheels of a car are rotating. Okay. So you might say that, okay, if things go around something, that is rotation. Is that the case? Is that the simple definition? But the way I have seen is that the car wheels are rotating, but the car is also moving forward. So rotational motion means something spinning and going forward. Is that rotational motion? Is it not? So what is the difference between rotational motion and normal motion, motion in a straight line? What is the difference? So again, you have already learned that motion can be of several types, and we have already seen what motion in a straight line is. That is, when we apply a force, an object moves linearly with a velocity v. So this is also known as translational motion, or simply rectilinear motion, because it is going in a straight line. So it is only motion in one direction, right? So what is rotational motion then? What is happening to the wheel of a car? So when a car wheel spins, let's say this particular wheel is made up of n number of particles. So let's say this is a wheel of a car and it is spinning. So spinning or rotation actually means that if there is a particle called m1 here, or m, random m, then if it can complete a circular maneuver around a fixed point, then we can say that that will be rotational motion. Okay, it is very simple definition. So where it is spinning about a fixed point with a fixed trajectory. So it is executing a circular maneuver, or it is executing a motion around a fixed point. Later we'll call it as an axis. So around a fixed point, it is executing a circular maneuver here in this particular case. And when that happens, we call it as rotational motion. But for a car, it is not just rotational motion, but rather it is also linear motion. So we can say that rotational motion plus linear motion, that is rotation plus translation motion. Rotation means a particle is rotating like this, and translation means it is going in a straight line. So rotation plus translation motion, translatory motion, together is known as rolling motion. So now you understand why people say, oh my god, a big wheel is rolling down the hill, or you are rolling down some plane. So what happens? You are rotating, but with along that rotation, you also have translatory motion. That is, you're moving forward or backward or sidewards. You're moving and you're rotating. So the combination of these two motion together is known as rolling motion. Okay, together is known as rolling motion. But sir, what's so special about this? We always know that even if we tie a stone to a string and just rotate it around, it is also rotational motion. What is so special about that? There is nothing special about that. We already know what rotational motion is. Then what is so important about this? So again, we are not just learning what rotational motion is, we are going to learn what are the mechanics of rotational motion, the nature of rotational motion, how we can perceive rotational motion. Because all the equations we have studied is for linear mechanics. For example, v is equal to u plus at. In that, v is final velocity or final linear velocity, and u is initial linear velocity, and a acceleration, again linear acceleration, and time is common for everything, but again terms are quite a bit different. Again, we saw momentum of a body, how momentum is imparted. Again, that is also linear momentum. Here everything is happening at a particular angle. That is, if this reaches here, then we can say that, okay, there is displacement. But how can you define that? It is not in the linear sense. It is at a particular angle. So how do you define that? How can you express that? So you already know that, okay, we can express that in terms of angle or angular displacement. So we need to have terms, analogous terms from linear mechanics to rotational mechanics. For example, I can say that in linear mechanics, let's say this is linear mechanics and this is rotational. Linear motion and rotational motion. So let's say linear and this is rotational. So if I say that, okay, there is a displacement from point A to point B, then we indicate that as S or X, as displacement or change in position. So we say that, okay, S is the displacement that is produced in linear mechanics. But how do we quantify that? How do we express that in angular terms? Again, if you look closely, we do know that, okay, here there is a difference in position. From A to B, something is moving, right? Something is moving, let's say spinning in this particular direction. So how do we signify or represent this particular displacement? We cannot use S, because if I say that, then automatically displacement is the shortest distance between 2 points. I cannot take distance also, because distance is a scalar quantity, displacement is a vector quantity. I need analogous of displacement. So how can you take that? So the actual way you can do that is simple. We just measure the angular displacement. So we already know that, we have already seen what angular displacement is, what centripetal acceleration, centripetal force, everything we have seen. We are just going to express that in rotational sense. That is it. So we do know that arc length, we saw one derivation in the previous chapter, that is arc length is equal to angle by radius. So we do know that in rotational mechanics, we use theta. That is how we represent angle to denote angular displacement. So we can say that analogous to displacement in linear mechanics, it is angular displacement in rotational mechanics. And the relation between theta and S is that theta by R is equal to S, from the equations we already learned in the previous chapter. So here we can say that, okay, theta by R is equal to S, that is arc length is equal to angle by radius or radius vector. Or we can simply say that theta is related to displacement like this. This is the relation between angular displacement and linear displacement. If you multiply linear displacement with the vector quantity that is R, position vector, then you will get angular displacement. So where is that radius? So this is that particular radius, R, from the center point to this particular point A. And when it reaches B, from the center point to this particular point B. So again, this is the linear relation between or conversion of angular terms into linear terms. So analogous to theta in rotational, we have displacement in linear. Just like this, how do we have for velocity, for acceleration? All that will be discussed very shortly, but generally I'll just tell you. So for example, here displacement is S. So if I divide displacement by time or rate of change of displacement, then I can say that it will be velocity. So this will be equal to velocity. So just like that, if I divide both terms by time, I can say that theta by t is, S by t is simply linear velocity, that is V into R. Now theta by t is now angular velocity. It is indicated by small letter omega. So this is one more relation, that is angular velocity omega is equal to V into R. So angular velocity omega is equal to linear velocity times radius or position vector. Analogous to linear velocity, we have angular velocity. Just like this, we can also have analogous to acceleration A in linear mechanics, we have angular acceleration, which is indicated by alpha, small letter alpha. So again, many quantities can be represented in this particular fashion. So in the coming sessions, you will actually see that certain other quantities also, that is, for example, force, which is expressed in linear sense. When it comes to rotational mechanics, it will be actually represented as tau, that is a T with a wavy symbol. So yeah, that is analogous to force. We'll study more about forces and other analogous terms very soon, but this is how the conversion process actually happens. So you should understand that for everything we express in linear terms, most of the terms have an analogous quantity in rotational sense also. So that is why we are actually learning rotational mechanics. So we will start this particular chapter. I hope you have understood the basic concept what we are trying to do. So we are going to find out certain laws, certain equations and certain properties of materials that are rotating. Okay. So the first thing is moment of inertia. So what exactly is moment of inertia? Sir, I have heard about inertia. It is the reluctance of an object to move. That is, an object won't change unless an external force is applied. Right? It has a tendency to remain in a state of rest or uniform motion. So that particular thing is known as inertia. But what is this moment of inertia? So just like when I told you before, every quantity will have an analogous term in the rotational sense. Here we are going to learn about mass. When mass is reluctant to move, we say mass has inertia, or simply mass is the measure of inertia of anything. Right. So just like that, when mass expressed in rotational sense, okay, when mass expressed in rotational sense, it is indicated as moment of inertia I. So it is indicated as moment of inertia I. Okay. So mass expressed in rotational sense is moment of inertia. Again, there should be a relation between these two quantities, just like displacement is equal to S times R. Angular displacement is equal to S times R. Angular velocity is equal to V times R. So mass will be equal to M times R. No. So the proper definition for moment of inertia is that it is the reluctance of a body to undergo rotation. If I am spinning an object, if I am trying to spin an object or rotate an object, the reluctance of that object to spin, the reluctance of that particular particle to spin is known as moment of inertia. So again, if I take one random particle, just like from the sand particle example, I am just taking one sand particle, one random particle I am taking. So if I am taking that one random particle, let's say M1 or M, small m, one random particle, and if I am making it go for a spin, let's say about a point, let's say this is the point, and I am making it go for a spin around that particular point, then obviously it is rotational motion. So if I spin a particle like this around a point, let's say this is the point, then I can say that the reluctance of that particular particle to spin around that particular point, to rotate around that particular point is known as moment of inertia. That is the simple definition. Now, what is the mathematical equation for that? We have to quantify everything. But just before that, you have to understand what this point is. This particular point where this revolution happens, this rotation happens around this particular point. So we can say that objects actually spin or rotate around a fixed point. We call it as an axis. So for example, this is an axis which is passing through the center of this particular rotational motion. You have already studied in your previous classes, that is 7th, 8th or 5th or 6th or something, that Earth is rotating about an axis where the axis is slightly tilted. So all that particular thing. There is no actual axis. It is just a mathematical axis we put in place so that we can actually form mathematical equations. We can define certain properties and all that. So for rotation to happen, two things should be there. There should be a particle which is rotating about a particular axis. So this particular thing is known as an axis, or more specifically, this is known as an axis of rotation. Any particle will only rotate about or around a particular axis. So this is known as an axis of rotation. Depending on the axis, you will have different type of characteristics. Sometimes it will be easier for the particle to rotate about this axis. Sometimes it will be easier to rotate when the axis is passing along the diameter. So there is two possibilities, right? One, it can pass through the center. One, it can pass through the diameter also. So there are several possibilities where the axis can actually be placed. So depending on that, the particle can actually spin easier or harder, which means it will be harder for the particle to rotate or easier for the particle to rotate. Now, why are we saying that easier or harder? Because moment of inertia is the measure of reluctance of a body to spin. So it actually depends on the axis also. It is not just the mass of the particle, but it is also the axis that is responsible for the rotational motion. So we can actually say that mass of a particle actually matters, axis of a particle actually matters. If I am saying it in terms of a particle rotating about an axis, I also have to specify how far is it rotating. Is it really far away? Is it really close by? That also I have to mention. So this measurement happens from the center of the axis. So I am saying that, okay, from this point to here, I am saying that, okay, there is a radius r. Now the particle m, or mass particle m, is rotating about an axis which is passing through the center, which is having a radius of r. So I can clearly say that the moment of inertia of this particular particle is given by the equation I is equal to mr square. If there is one individual particle, let's say there is one individual particle which is rotating about a particular point like this. So this is the axis which is passing through the center, and one particle is rotating like this. The reluctance of this particle to rotate along this particular axis is expressed as moment of inertia. The easiest example would be tying a stone to a thread and rotating it around. You have to perfectly know that the string is now acting as the position vector, the stone is now acting as a simple mass particle, and your hand is now acting as the axis. So that particular motion is now quantified as mr square. Now again, this is only for one such particle. If I am taking, let's say, the case of a ring or that particular stone also, if I am taking a stone, let's say this is a stone, then we cannot just say for one such particle. We have to say for the countless n number of particles which is rotating in this particular rock or stone. So for that, again, we know that if there is a system of particles, we have to take the summation. But in this particular case, just taking the summation of mass alone is not enough. There is also radius, which is measured from the center of the axis to each particle. So if I say that the net moment of inertia of that particular stone is equal to n number of particles are there, then I have to take m1 r1 square plus m2 r2 square plus m3 r3 square plus so on up to mn rn square. Like that I have to take, or mi ri square, like that I have to take. So instead of taking individual quantities like this, what will you do? We will just take the summation. That is, instead of writing it as long like this, we'll just say that, okay, summation over I is equal to 1 to n mn rn square. We can write it like this. Or if you don't want n in your NCERT textbook, it is given as I. So we can just represent it as mi/ri square. So the net moment of inertia I is equal to mi/ri square. If I called summation over all the I particle as capital M, then I can simply say that summation over all the R radius vectors will be equal to capital R. So simply I can just say that, okay, generally I is equal to capital M R square. So this is the moment of inertia of a particle which is executing a circular maneuver around a fixed point like this. So remember this shape, because the shape will become later useful. Again, the only difference is that this is for a single particle, this is for a system of particles. So this is how you actually express moment of inertia. So from this you can actually measure or understand, okay, what all quantities are moment of inertia depending upon. So here the moment of inertia is depending upon the mass of the particle, the radius from the axis, and axis of symmetry itself. If it was slightly different, it will be more harder for us to spin. If you spin a rock tied to a string like this and like this, it is different. So depending on the axis of rotation, it will be either easier or harder. So axis of rotation is one thing, mass is one thing, radius is one thing. Depending on the radius, if R increases, reluctance to spin, that is moment of inertia, increases. So that is also one factor. And mass distribution. So also one more factor is mass distribution. If this rock is not uniformly distributed and most of the mass is concentrated like this onto one end, it will be extremely difficult for us to make it spin. If it is evenly distributed, like in the case of a disc or in the case of a spherical ball, it is easier for us to make it spin. If it is not evenly distributed, it is much more harder for us to make that object to rotate. So based on that, we can say that mass distribution also actually matters. It also affects the moment of inertia of this particular rotation. So the only thing you have to remember is that moment of inertia is indicated by I, which is given by the equation mr square generally, because depending on the axis and the material, we have to slightly make some modifications on this. That we'll see very soon, but for now know that moment of inertia is generally represented as mr square. That is when we consider a particle which is rotating around a fixed axis in this particular manner. That is, the axis is passing through the center and the particle is rotating around that particular axis. Then we can say that, okay, moment of inertia of that particular particle is given by mr square. So it will depend upon the mass of the particle, mass distribution of the body, radius from the axis, and how far the object is spinning from the axis. That particular things also affect moment of inertia. And moment of inertia is nothing but the measure of reluctance of a body to undergo rotational motion. The measure of reluctance of a body to undergo rotational motion. Understand, just because there is inertia, it is not analogous to inertia in linear mechanics. In linear mechanics, if we write inertia, we have to write rotational inertia in rotational motion. Rotational inertia in rotational motion. That is, if we say mass in linear sense, then we can say moment of inertia I in rotational mechanics. So understand that moment of inertia is actually analogous to mass in linear mechanics, or simply these are the rotational analogues of the linear quantities. For example, inertia becomes rotational inertia, mass becomes moment of inertia. That is how the change happens. Just because there is a change in name, don't get confused. This is not inertia, this is moment of inertia, which is a different quantity. We have also moment of force. Moment of force is known as torque. So it is just an easy conversion. You don't get confused with all the terms. So in this session, we have to learn one more thing. Unfortunately, you have to by heart this, because there is nothing mentioned about how these quantities actually came into place. We don't have to do the mathematics, we don't have to do the integrals, we don't have to do any derivations in order to find this particular moment of inertias of different bodies. The only thing you have to study or understand is that moment of inertia of these particular bodies is given by these particular equations. But again, so we'll look at how the moment of inertia of different bodies look like. So we can actually let's start from thin circular ring of radius r and mass m. Let's keep the rod there. I'll explain it at the very end. But let's see. So thin circular ring of radius r and mass m. So the axis is passing through the center and perpendicular to its plane. So its moment of inertia is given by mr square. So what does that actually mean? So we have a thin circular ring. A thin circular ring means this is the ring. Ring means the center is empty and there is only boundaries. So the mass is concentrated around this particular boundary. So this is a thin circular ring. Now, where is the axis? The axis is actually passing through the center like this. Okay, this is the axis, which means the rotation happens like this. In this fashion, it is rotating. Now, what is the moment of inertia? It is indicated as mr square because again, if we take one random particle here, let's call it as m, it is rotating around this particular axis. It is what we just proved earlier, right? It's the same type of motion that I just showed you earlier. And we just know that I is equal to mr square. Simple. I is equal to mr square. So for this particular arrangement where there is an axis passing through the center perpendicular to the plane, for a thin ring, circular ring, we can say that moment of inertia is equal to mr square. See, one axis is passing through the center, one particle is rotating it. For that, we learned earlier that I is equal to mr square. That's all. And now, this is not the only rotation possible. If I can take this axis and tilt it, one more type of rotation is possible where the axis is actually passing through the diameter of this particular ring. Right? Not through the center, but rather through the edges or through the diameter. Now the ring is spinning like this. Earlier it was spinning like this. Now each particle on this ring is spinning like this. The ring itself is spinning like a thread or needle is passing through that. So it is spinning like this. So what will happen to the moment of inertia? So actually in that particular case, moment of inertia becomes half. So it is mr square divided by 2. That is, again, see, you have to imagine it rotating 90 degrees. So because then the image will be clear. Because right now you're just saying that, okay, it is passing through the center. That is the same case. It is passing through the center perpendicular to the plane. So then the moment of inertia is given by mr square. Now again, if the axis is passing through two ends, that is along the diameter, passing through the diameter, then moment of inertia will become half of that particular quantity. So mr square by 2. Now that is the case for a thin circular ring. Now if we are taking a disc instead of a ring. So what is a disc? You might have seen CDs, right? So imagine the CD without any hole in it. Imagine that throwing discs. So it will be just completely filled circular things, circular discs. So again, there won't be any empty space. That is, this will be completely filled. Mass distribution is now much more even. So you know that mass distribution actually affects the moment of inertia of every object. So the mass distribution also affects the moment of inertia. So what happens now? In the earlier case, we considered there was a thin circular ring through which the axis passed through the center perpendicular to the plane. Now the axis is passing through the center perpendicular to the disc. Now the center is completely occupied by mass particles. Now we are trying to spin a disc like this. If you take a book or plate, and you might have seen friends rotating it like this. So if I am trying to rotate it like that particular plate in my hand, then what will be the moment of inertia? So it is because of this evenly spread out mass, it just so happens that moment of inertia will become right half. That is just like in the case of a circular ring where axis is passing through the diameter. Just like that, for a disc, if the axis is passing through the center, it will be half the moment of inertia of that of a ring. So that is, for a ring, it will be mr square. But if it is a disk, it will be mr square by 2. It will be halved. So again, one more situation is there where an axis can pass through along the diameter. So we can just use logic and say, because again, for a thin circular disk, it was mr square. When it became the diameter, it was mr square by 2. For a circular disk, it was mr square by 2, which means along the diameter, automatically it will be I is equal to mr square divided by 4, half of that. Right? Here it was mr square, that became mr square by 2. Just like that, this mr square by 2 will become mr square by 4. No other difference is there. Again, now the last things we have to study is just we have a cylinder. Let's imagine a flute. Let's imagine a flute with no holes in it. So that particular object, and the axis of symmetry is like this. This is the axis of symmetry. For that particular case, we can say that it will be mr square. Now, why is it mr square? For a ring, you said mr square. Okay, we understood. We agreed to that. For a disk, you said mr square by 2 because of mass distribution. Okay, we agreed to that also. But for a cylinder, why is it mr square? Just look from here. Look from here and look at the cylinder. The opening is almost like a circle, right? It is almost like a thin circular ring through which the axis is passing through the center. If I am looking through here. So imagine it like that. So because of that, it will have the same moment of inertia that of a thin circular ring. The only difference is that that ring is now slightly extended. So the ring is slightly extended. The middle part is almost empty, right? It is always empty. So if we look at like this, I can only see a ring which is rotating about an axis where it is passing through the center. The only difference is that this ring is now stretched like this. So it will have the same moment of inertia. So with that same logic, we can say that for a solid cylinder where completely mass is filled, again, it will be same as that of a disk. So this was mr square by 2, then automatically this will also be mr square by 2. Because if I look at like this, it is a solid sphere completely filled, which means it looks like a disk that is being stretched out. So again, it will be mr square by 2. Now, in the case of a sphere, that is, if you have seen basketball players or football players just rotating a ball on their fingers, then you can say that the axis is passing along the diameter. Again, if you take any axis, it will always pass through the diameter. No matter which axis you take, it will always pass through the diameter, and its moment of inertia is given by 2 by 5 mr square. 2 by 5 mr square. So that is the moment of inertia of a sphere. So we can actually calculate the moment of inertia of Earth, assuming it to be a sphere. It is not a sphere. It is actually an oblong or an ellipsoid, but again, we can also call it as, assume it as a perfect sphere, because nowadays we say that there's a penguin, assume it as a perfect cylinder. Like that, like the meme, we can say that. And finally, if you are taking a thin rod, a rod means a rod like this. So if I'm taking that particular rod and I'm assuming an axis which is passing through the center of that particular rod. So if I'm spinning it like that, then the moment of inertia for that will be ml square by 12. Why L square? So instead of R, we are measuring it in terms of length. So since we are measuring it in terms of length from the axis, that is why we are actually using L. That is the only case. No other explanation should be there. So we just use length. So ml square by 12. So these are the moment of inertias of different quantities. You don't have to stress too much. You just have to understand the basic concepts. So from the next class, we'll actually start some problems and go through in detail about how we can approach rotational mechanics. So I hope you have understood the introduction class or the first topics, rotational motion. We'll only be focusing on certain concepts and equations that is important for the examination. So I'll see you all very soon with the new class. Thank you.